Apollo 11 slips behind the moon. On Earth, the voice channel drops first. Then the trace on the monitor goes flat. Mission Control keeps looking at a screen that has nothing left to return. The spacecraft does not stop. It keeps sliding along the far side, carrying living astronauts through a part of the mission Earth can no longer hear, see, guide, or correct. For roughly 45 minutes, the silence belongs to the people on the ground. That is the first strange part. Lost contact does not mean frozen time. It means the crew is alive inside a moving machine, while every direct confirmation has disappeared. A routine blackout should feel like waiting. But the flat line changes what waiting means. Earth has not lost the crew. It has lost supervision. Apollo 11 keeps moving behind the moon. The radio channel stays silent. Instruments continue updating. Panel lights remain active above the darkness of the lunar far side. For a moment, everything appears normal. Then the real consequence becomes visible. Houston has nothing new to correct. The spacecraft has crossed into a region where Earth cannot reach it directly. The moon now sits between command and crew, physically blocking the radio line of sight. Help still exists. It is simply on the wrong side of a wall. That changes the meaning of the blackout. If lost contact were harmless, nothing important would depend on it. Instead, every layer of immediate decision-making moves on board. Responsibility shifts inward. The crew becomes the only reachable authority. The far side is not empty, it is unreachable. And that means the problem is no longer the silence itself. The problem is everything's still happening inside it. A checklist sits open under the glow of cockpit instruments. Displays continue stepping through planned sequences. Nothing appears frozen. Nothing appears lost. In fact, this was expected. Apollo missions pass through this communication shadow again and again. The blackout was not treated as an accident. It was built into the mission. Long before the spacecraft reached the far side, procedures were already waiting for it. The crew follows the plan. The onboard systems continue their work. The lunar horizon remains dark and unchanged as the spacecraft moves beyond Earth contact. The silence has become part of the design. But notice what changed. Apollo 11 is no longer relying on live supervision. It is relying on decisions made before the silence began. Confidence now rests on prediction. And that creates a different kind of dependence. If the planning is correct, the spacecraft should return exactly as expected. But from this point forward, every expectation is traveling through the blackout with it. On a screen, the orbit can look clean. A thin line bends around the far side, smooth and predictable, as if the spacecraft is simply following the path already drawn for it. But the moon below is not pulling evenly. Hidden regions of stronger gravity, called lunar mascons, affected orbital predictions. They did not need to be seen to matter. They only had to tug slightly while Earth was unable to watch the change happen. The line keeps bending. Mission Control waits for the signal to return, but until it does, the expected path is only expected. It has not been confirmed. That is where the planned blackout starts to break. Procedure can tell the crew what should happen. It can tell Earth when the spacecraft should reappear. But prediction is not control. And if the path is changed inside the silence, correction may arrive after the useful moment has already passed. Apollo was only the beginning of that problem. The farther a mission travels, the weaker real-time supervision becomes. A signal between Earth and Mars can take many minutes to arrive. By the time a warning reaches a crew, the moment that required intervention may already be over. The blackout behind the moon was short. Future missions may not be. On Earth, the signal trace rises again. The edge of the spacecraft clears the lunar horizon. Mission Control has a voice channel back. The screen is no longer flat. For a moment, that feels like safety. But the return changes something colder than the loss. The return signal proves something simpler. The spacecraft survived a period Earth could not observe directly. And that distinction matters. The blackout never guaranteed a failure. What it exposed was a limitation. During the Apollo era, engineers discovered that hidden concentrations of mass beneath the lunar surface, later known as lunar mass cons, could gradually alter orbital predictions. The effect was small. But small effects mattered. A spacecraft could follow its planned path and still emerge slightly different from what earlier calculations expected. The signal returning did not restore certainty. It only restored visibility. The lesson did not stay confined to a single blackout. Apollo missions repeatedly revealed how small uncertainties could accumulate while spacecraft operated beyond direct observation. Navigation corrections, orbital predictions, and landing preparations all depended on information that could never be monitored continuously from Earth. The farther humans traveled, the more important that problem became. Because distance was no longer just delaying communication. It was limiting supervision itself. The danger was not created by a single failure. It emerged from small changes that accumulated while nobody on Earth could watch them happen. That is why the lunar blackout matters beyond Apollo. Mars missions can face long, one-way communication delays. A message may take many minutes just to arrive. By then, the moment that needed help may already be over. So the flat signal behind the moon was not just an Apollo problem. It was a preview. The farther humans go, the less Earth behaves like command. And the more survival depends on decisions made beyond Earth's reach. The blackout behind the moon was never just a communication problem. It was the first warning that exploration eventually becomes trust.